All right, so living on planet Earth, we're sort of familiar with Earth's gravity field. We're made of mass, a region of space where massive objects experience a force as a gravity field. Earth has an electric field, but because the mass that we're made of has both protons and electrons in sort of equal charges, we're neutral. So we don't get pushed around by Earth's electric field. We have to sort of create an electric field by depositing charges somewhere. So like when you rub a balloon on your hair, you're basically depositing charges onto your hair, and then those charges repel each other, so your hair sort of sticks up on end. Here we're going to use a similar sort of idea where there's some felt paper at the bottom of this. You can see with this clear tube here through that there is an elastic band, and then so when I turn the motor on, it's going to sort of rub against the felt fabric down here, take electrons from it, they'll travel along here, and then there's a little metal sort of like honeycomb-like thing that the charges can conduct onto, and then they'll be deposited onto the surface of the sphere here. So you know a lot of electrons piling up on this sphere. When you've got a bunch of charges in a place, there's going to be an electric field around it. Okay, so this thing isn't connected to that. It's just sort of, it's got a little thing though. So I could actually bring this surface closer to this one. Now, some of you might recall that an electric field is the voltage divided by the distance, right? And so there's going to be a certain voltage, a potential difference as we deposit sort of charges here. And as I decrease the distance between this, I'm making what? The electric field between them stronger and stronger and stronger. So air, the air that's between these surfaces right now, is a really good insulator. Electricity will not tend to conduct through air. But you can get a strong enough electric field to force the charges to conduct through, even though air is a good insulator. So that occurs at what's called the breakdown voltage. And for air, it's about 40,000 volts per centimeter. And so when you observe lightning striking, you basically, there's an electric field between the clouds and the ground that's intense enough that we can actually conduct electricity sort of across what normally is a really good insulator, the air that sort of exists between the clouds and the ground. So we've all seen lightning strike, and we're going to see it right now. Lights. Thank you, lights. Stand by. There's a nuclear furnace like 93 billion miles away. The byproduct of all of that nuclear fusion is like light and heat, which usually is not too bad as an earthling. But sometimes you don't want the light trying to observe the breakdown voltage of air. And I see some, classrooms on campus where teachers just black out the windows. They're just, it's like, oh, yeah. Look through the windows. Light sometimes. Not today. So that's slightly darker, I suppose. All right. All right, so maybe you saw that little bit of lightning strike there, and you heard it, right? So that's, a little thunder, right? So lightning is so hot that it heats up the air, and the air crashes into other air, and so we hear that so you hear sort of the conduction also. So there is a little demonstration of an electric field, and what you can sort of achieve with it. When we cut the lights back on here. What else maybe can we see with this? Okay, so I mentioned that your hair stands straight up on end, rubbing a balloon on it. Here I have some synthetic hair in the form of ribbon. And so you can imagine that as I turn this back on, again, you hear there's a motor, right? I have it plugged in, so that's where it's from. Going to deposit the charges. The charges will then conduct onto the ribbon, and they should repel each other. So we would, hypothesize something like that going on. Let's have a look. Always so nervous when I'm going to turn it on. All right, so there's that. How about 3-volt punch? Oh, remember, taking a lot of 3-volt punches this year. Here we go. Mindful to do more 3-volt punching throughout the year before we get to electric fields. So here's some 3-volt punch papers. I'm just going to kind of sprinkle them on top here. So the same idea. We want to deposit charges. Oh, a staple made it in there. Oh, that makes us like the scientists like, hey, we can test that. What would happen to the staple? We put it on there. Let's try it out. Why not? All right, so pieces of paper, so your charges deposited onto them, and then they're going to repel. And so you kind of get an idea about where we're drawing field lines. What does the field look like around this thing? Sort of like radial lines that extend out. As charges get deposited onto this, there's an interaction, sort of between them. So let's see what happens to the pieces of paper and a piece of metal. So I guess it's going to conduct along. Well, let's see. In science, we test things. So eyes right here. If you want to see this in person, otherwise, like it's projected on the screen up there. Again, it's being repelled. Could we harness energy in an electric field somehow? So the way that power plants typically work is we turn water to steam somehow, and that steam has kinetic energy, right? Because it's a gas, and so the steam is a turbine. The turbine can convert that kinetic energy into electrical energy by sort of cutting across a permanent, two magnets that have an electric field, and so when you cut a coil across that magnetic field, it induces current. So it's electromagnetic induction. Basically, what it comes down to is if we can turn water to steam, right, then we can harness that kinetic energy of the steam. And the ways that human beings have thought to turn water to steam are by mining fossil fuels out of the ground and burning them. So like we burn oil and coal and heat up water to steam. We mine radioactive material out of the ground and start nuclear reactions that get really hot. So there's nuclear power plants. Again, just the goal is turning water to steam. And if you've got a better way to turn water into steam, then I'd like to hear it, like the sun or something like that. So maybe a solar thermal power plant makes a lot of sense. In fact, in Martin County here in Florida, there is a natural gas power plant that they converted to. With the sun shining, they're going to sort of have these parabolocylindrical sort of mirrors that will harness the sun's energy. Again, the goal is turning water to steam. So if you do that with sunshine, we don't need to mine radioactive, fuel out of the earth and have radioactive waste. Not that, nuclear energy isn't an important piece of a sort of diverse and broad energy portfolio. But we want to be like, there's no shortage of energy in the universe, but human beings are, in the dawn of the 21st century, not too smart about how we can harness the abundance of energy that's sort of here. So something to sort of think about. So here we're going to see, can we get this thing to spin from the electric field? And so again, charges being deposited sort of here, this thing is free to move. And so if we can get this spinning, you might be able to think about, okay, harnessing sort of electrical field energy, getting turbines to spin, right? We know if we can get a spinning turbine, we can induce electricity. So, well, this thing itself is plugged in, takes a lot of energy to generate this, and I'm sure we're not getting as much energy out over here. That's true. So it's just a way to sort of prove the concept of we can get sort of motion from the electric field. Maybe there's a way to harness natural electric fields like lightning and things like that. That's really tough because that's hard to predict. But you know, again, this is sort of a proof of concept. So I'm going to try to hold this here and not get myself shot. Yeah, it's still taken back even after it's turned off. So sometimes like computers that have been for a long time still have charges in their components. If you're ever doing any like hardware work with the computer, make sure it's been off for a while, right? Won't get sort of shocked with. Many students that take physics also take psychology, and many students are familiar with Stanley Milgram's famous psychological experiment, where it was really an experiment about authority and how, you know, people will tend to just listen to others in a position of authority almost blindly. This is sort of after World War II, where a defense, you know, was kind of like, well, I was just following orders, I was just following orders, all these war crimes, and you know, is it wrong? What is the sort of psychology of that? How likely people will be to sort of blindly follow authority? So in Milgram's experiment, there was an actor that was hired, right? You're probably familiar with this as you take psychology. An actor that was hired, so nobody was actually getting shocked, but the person who was sort of the test subject was told that they were going to ask, you know, the person on the other side of this wall some questions, and if they got it wrong, the answer wrong, they were going to administer a mild electrical shock to them that would, you know, ramp up in intensity, you know, as they continue to miss questions. And so the person wasn't, you know, was an actor on the other side, and you know, they kept on missing the questions, and then the shocks would get, you know, more and more intense. And you know, the person would be saying, oh, "Please stop! I have a heart condition," you know, kind of telling them, "Hey, stop doing this." And the person who's administering the shocks is looking at the, you know, the guy in the lab coat with the clipboard, who's just saying, "Yeah, please continue. You know, that's fine. Let's." And so, I think it was, I forget the exact results. It was like 70% of something people took the experiment all the way to where they killed, you know, the person that was, you know, was the actor. They administered, you know, shocks until eventually they said, "Please, you know, I can't take it anymore." And then, you know, nothing. So now there's silence. So it's like, oh no, I didn't know. And so it's just like, would people be willing to sort of say, "Hey, I don't care about your science experiment. I'm not doing this. I'm not going to be one to administer shocks to somebody. They're in pain over there." And again, most people weren't willing to do that. Weren't willing to sort of go against the authority figure. You know, the guy in the lab coat, obviously this is important, you know, and they're doing a whole science experiment. I don't know if you could do a similar experiment, you know, today, how the ethics of that sort of work with the test subjects. I think it's unethical to do that to the people that were sort of the subjects of that experiment, to make them think that they were, you know, killing somebody else on the other side. But one of the people that was involved in the study was, you know, worked with electricity, and he was the one of the ones that refused because he says, "I know what it's like to be shocked. You know, I felt an electrical shock before. Moreover, I know what it's like to anticipate being shocked. It's almost worse, like the shock, just get it over with. It's like, oh, I'm about to get shocked. So every time I turn this off, like, is it going to get me? You know, get a little shock there. And, you know, just a little brief moment of pain, but then it quickly goes away. And it's perfectly safe. Right. So with that in mind, and electrify myself here. Now I'm standing on Earth. And so you ever heard like, oh, this is grounded, okay? The Earth is an infinite reservoir for electrons. And so the electrons will go through my hand, my body, into the Earth, through my feet. And again, the Earth will gladly accept as many electrons as we want to give it. So really nothing's going to happen. Let's do this. I always want the shock to go to this thing instead of like me. So, but anyway, you saw there, got my hand on there, turned it on, nothing. I'm grounded, right? So the earth is grounding me. What I need is a good insulator like air to meet my feet in the earth. Now I will electrify myself. Be careful, but I'm standing on a plastic chair, and then there's metal legs, and sometimes the charges will conduct through my shoe and into the metal leg, and that really hurts. You feel like your big toe there. So maybe I could find a wooden stool rather than a metal leg chair here. So it's not too bad. It's a mild painful shock. Also a pretty good insulator. Air, good insulator. All right. I can't anticipate anything going wrong. Oh. It's kind of always a joke. You gotta get a haircut and you never like take enough off the top. And I think I got the last trip, but it's just way too much off the top. So you'll see sort of me becoming electrified here. My hair's not long enough. Oops, the plastic chair, whatever. All right, so we'll off the lights. Any volunteer that's brave enough, you thought it required some bravery to offer an answer to the practice calculation. It would take yet even greater bravery to come give me a high five. Okay, just a moment. So anybody that's willing to do that, okay, we got it recorded for posterity, for the benefit of our e-learning colleagues. It's gonna hurt, okay? I'm gonna tell you right now, it's gonna administer a mild, painful shock to you because I'm gonna be electrified, all right? You're gonna be grounded. So what do the charges wanna do? Path of least resistance. They're gonna go through me and they're gonna jump into you. And you're gonna feel that, okay? When that happens, and I'll feel it too. Like we'll both get a little shock here, all right? No one wants to do that. No one's brave enough. I don't think I can require you to. Like we're learning physics here. Everybody's got to get shocked. You know, it's like, you know. But if you want to, okay, you can. So we'll make that available to anybody that wants to. If not, maybe you can see like my hair standing up a little bit up here. It's not going to be that impressive. So we'll go left hand. You can either do like a ET kind of fingertip high five. All right. Not really high five. And you do an actual high five. Okay. So come on down if you're brave enough. Here we go. Fine thing over there. I thought, you know, maybe I could do it a little fast. I could do that. All right, that's some Scott on your chance. You know, with the rest of your life in regret. Just that. I thought I had a chance right from there. Wow, gotta make up college now. And here, and maybe you can check the video. So I think I recorded last semester some participation with that. What I've done in the past is have a chain of students. Like everybody get up on a chair, everybody stand on a chair, and then the last person is grounded to me. really get the bad shot because the charges are sort of building up and everybody can kind of like, we're all holding hands. Everybody feels electrified, getting to feel it if you're electrified. And then the last person bears the brunt of all of those charges sort of discharging through into the earth. So, and everybody feels it. It's great fun. Anybody want to come up here and try this? And not give you enough time to try to put your hand on here and just let it electrify you. Volunteers to do that. You can do it both on the earth where it won't do anything, or you could stand on a wooden stool or a chair and see if it conducts to your feet. So I want to make that available to anybody. You learn went to school today. Can't do something awesome. So anyway, electric field, like this is a Van de Graaff generator. It's named after Dr. Generator, who invented it. And it's just a way to sort of explore electric fields, right? So sort of practical purposes other than like teaching, sort of demonstrations. But there is a lot of practical utility in creating an electric field like in a wire, in a circuit. Because then we can exert forces on charges like electrons that are in the wires, like copper wire, and we can get the charges to power our devices. So if you think about like a circuit breaker box that's probably somewhere in your house, and all the circuits that are sort of powering the electronics in your your home are connected into that. So there's many circuits that are in buildings that power everything electronic, including like the audio-visual equipment that you're using to communicate right now. So again, the practical importance of this cannot be overstated.